Hey, today I'm going to show you guys how to calculate the volume using calculus, calculate the volume and the lateral surface of a right cone. And why do I want to put these two videos on these two subjects on the same video? It's going to be a long one because it's very important, the different way of thinking of how you calculate the volume of a cone and how you calculate the lateral surface of a cone. It seems that they're the same, but there's a twist to it. Okay, so I decided to do this. I decided to use this 3D animation program here to make it easy to visualize what I'm talking about. So this is the cone, okay? And how do we calculate the volume of a cone like this? Well, you have these discs over here, okay? This is one disc, and here's another disc, and here's another disc, okay? I can move these discs, and you're gonna see that they adjust, all right? Okay, so I have all these discs in here, and if you put infinite discs together, you're gonna put a stack of discs. First of all, why is the cone upside down? Because it's gonna make the math easier later to integrate, okay? So you have one disc, and then you have another disc, and another disc, and another disc, and another disc. You're gonna have the volume of a cone. Okay, the volume is what's inside the cone here. So you have this, the base, okay? I can move the base, and then you're gonna see that the cone in there is empty, okay? You care about the space when you're talking about the volume. So I'm just gonna put this here, okay? Now, how do we calculate the volume of the cone? We're gonna calculate the volume of the cone the following way. Here I made an orthographic projection of the cone. So you're seeing the cone through an orthographic camera. Okay, the orthographic camera is the one that's gonna throw away, it's gonna discard the depth axes. So let's just say they have the x and y axis. You're gonna worry about those, or you're gonna worry about the x and z axis or the y and z axis, but not, you're always gonna discard the depth one. So you're not going to have any parallax problem with perspective and things like this. Okay, so how do you calculate the volume of the cone? Everything that's inside here, yeah, all the stuff that's inside here. How do you do that? Well, you're going to calculate the area of this disc plus the area of this disc plus the area of this disc right here plus the area of this one. Okay, that's what we're going to do. And this is just going to work. So how do we do that? Well, you have infinite discs, okay, whose depth, whose thickness is infinitely small. So their thickness are infinitely small. And when you add them together, it's going to equal the volume of the cone, right? So how do we do that? Well, it's going to be, what's the area of a disc? It's the area of the circle. So it's going to be the integral, okay, with respect to y, because you see the apex of the cone is right here at the origin. So you have the height of the cone, and you have the radius of the base of the cone. Okay, so we're going to integrate this disc plus this one plus this one plus this one plus this one, all infinite discs, until we have the entire volume. So the integration is going to be from 0 all the way to h, okay? When y is 0, all the way to y with the value of h in here. I'm just going to put this here, okay? And it's just going to be what? Pi r squared. But what is this r here? What's the value of r for a given disk? For example, let's just say that I choose this disk in here. What's going to be this r? What will be this distance? Well, this distance is going to be the value of x to the y, okay? Because since you're going to be integrating with respect to y, then you have to, well, let's just say, instead of putting an r here, I'm just going to put an x squared y, because that's the value, okay? So when you have from here to here, what is this dimension? This dimension is the same dimension as the x-axis. And when you have this value here, it's going to be the same dimension of the x-axis. So it's the value of x for this disk at this height, for this y here, and for this y here, okay? So, but we can't leave the x like this. We can't just do pi x squared dy, because we got to make this x become a function of y, all right? We got to express the x as a function of y. So I'm just going to put to the side here. I'm just going to say that what is x as a function of y? Well, you see this stuff in here? This is what we call, some people call this g. That's going to be the length of the side of the cone. Okay, this thing is fixed because the base is not going to change its radius and the cone is not going to change its height. So r divided by h is always going to be the same no matter what the height of the y in here is. R divided by h is always going to be the same. So how do you find this value of x here for this y? Okay, so we can say that x equals r divided by h times y. If you just plug in a couple of values here into this y, you're going to see that it's true. Okay, let's just say that y equals h. You're at this point right here. Okay. What is the value of x here? It's r. So let's just plug in x equals r divided by h times h, okay, because y has the value of h in here. It's at this height. So you're just going to cancel these two and x equals r. Does x equal r in here? Yes, it does. Okay. Now let's just plug in another value for y. Okay. So let's just plug in the value of 0 for y. If you put 0 in here, you're going to multiply this by 0, so it's going to be x equals 0. Now, when y is 0, is x equals 0? Yes, it doesn't get out of here. I mean, it doesn't come over here. Okay, it's the apex, so it's right here at this point. So that's how I relate x to y. Okay, x equals r divided by h times y. Now, I know from experience that we're going to need dx too. Well, let me think here. Are we going to need dx? Well, let's just go with the flow for now. Okay, so this is going to be pi x squared, but we can't just put x. We have to relate x with y. We got to relate x to y. So if it's x squared, what's going to be? It's going to be r squared divided by h squared times y squared dy. Okay, so you're going to find this disk, then this disk, this disk. You're going up in the y direction. That's why you're integrating with respect to y. Okay, now you have all this thing here. Okay, this is not going to change with respect to y. I mean, does pi change? When y is 100, is pi going to be 5? No, pi is always approximately 3.14, and r is going to be the same because this r is the radius at the base, doesn't change. This height is the height of the cone, it doesn't change. So these things are constant, so you can just take them out of the integral. So you can say pi r squared divided by h squared, okay, times the integral from 0 all the way to h of y squared dy. Now I'm going to continue this thing here, okay. So what are we going to have? We're going to have pi r squared divided by h squared times the integral of y cubed with respect to dy. What's going to be? It's going to be y squared with respect to dy. It's going to be y cubed divided by 3. When you plug in this whole thing here, okay, you got to plug in, it goes from 0 all the way to h, right? Because these are the limits of integration. So when you plug this stuff in here, you're going to have pi r squared divided by h squared times, you plug h in here, so you're going to be h cubed, okay, oh man, h cubed minus pi r squared divided by h squared. Now you're gonna plug the 0 in here, okay? Oh yeah, it's h cubed divided by 3. I can't forget about that. H cubed divided by 3. And this one here is gonna be times 0 cubed divided by 3. I'm gonna continue the thing in here, okay? Now you have an h squared here and you have an h cubed here, so you simplify this with this one. And what are you left with? You're left with, well, this term in here is just going to be 0, because 0 cubed is 0, divided by 3 is 0, and 0 times everything is 0, so don't worry about this stuff. So what are you left with? You're left with pi r squared times the height divided by 3. There's something peculiar about this. You know, whenever you have something that's... you start with something big here, and it just goes linearly small as it goes up, or if it's upside down, okay, you're gonna have something here, and it linearly grows smaller linearly because this side is linear. Always the volume is gonna be, let's just say that you have something like this, okay, and now you have a pyramid or a cone, or it doesn't really matter what. Have this. Now the area of these bases are the same, and the height is the same too. The volume of this thing here is always going to be 1/3 of the volume of this. So let's just say you have a cone in here. If you had a cylinder with the same height and with the same area of base, meaning the same area of the circle, the cylinder is going to fit three of these of this volume here. So if you have a cup in this format, and usually they make cups with this format, and then you make a cup with a cylinder format where you're going to have the same where the lid and the base are going to be the same in here, the same area, you're gonna be able to fit the amount of water in this cup here 3 times as much in the cylinder. Yeah, it's kind of complicated. So you have a cone cup here, and you have a cylinder cup. You fill this one with water once, twice, 3 times. You can pour it in. Okay, it's gonna be always 1/3 of the volume, because pi r squared times h equals the volume of a cylinder with the same area of the base here and the same area of the lid here. But in this case, you're linearly growing smaller as you go up or down. Okay, so the volume of this is always going to be 1/3. Okay, now that's the fun part. Now here we're going to start the complicated part. This is a new slide in here. Okay, so let me show you guys what I'm talking about. We were able to prove, okay, find the formula for the volume of the cone if you just add these discs in here. Add one disc, another. Of course, these are not infinite discs. Okay, I just spaced them out to make it easy for you to see for visualization. But what you have are infinitely discs in here. They are infinitely close to each other, and you add one and another and another and another and another and another. You're gonna find the volume of the cone in here. Great. Now let's just say that you see this cone is a solid object. All right, it's filled. You actually care about the volume in there. Now in this case, we're gonna calculate the lateral surface of the cone. So you don't care, you see that the cone is empty, okay? You don't care about this internal space. You just care about the area of this surface here. How much is it? The area of the lateral surface, okay? So how do we do that? Well, if you add a bunch of discs in here, you're gonna get the volume. If you add a bunch of rings, which are just the circles, the outer circles, you're gonna have the lateral surface, right? Wrong. It just doesn't work this way. And then you go like, oh, wait a minute. I mean, if you add a bunch of discs, you have the volume. How come when you add a bunch of rings, a bunch of circles, you don't have just the outside of the cone, which is what I want, okay? It should make sense, but it doesn't. Thank God it doesn't. Now I'm gonna show you guys why. Here we go again. When we're adding, okay, this is the orthographic camera here again. When we were adding the area, okay? So you're gonna care about, let me just grab another color here. I think I'm just gonna grab black, make it easy to see, yeah. So when you're adding this stuff, you're gonna add this entire area, okay? And then you're gonna sum with this entire area in here. And then you're gonna sum with this entire area in here, all right? Now, every time that you're doing that, let me just grab another one. I think this one here is gonna be good. This color. So you're adding these things here, okay? This one plus this one. And here, okay. Let's try it again. So you're adding this one plus this one. I know it's hard to see, but it's tough. Plus this one in here and plus this one in here. This is to find the volume, all right? These are the discs, the areas of the discs when you see the cone through an orthographic camera. Do you care about this thing here? No, you actually discard it. You discard this one, and you discard this one, and you discard this one, and you discard this one. You're discarding all this stuff, okay? Now, when you're adding the rings to get the lateral surface of the cone, what are you doing? You're going to get the circumference of one ring, which is the circumference of the circle, which is 2 pi in that particular r, plus 2 pi in the other particular r, plus 2 pi in the other particular r. What are you doing? You're adding this part right here, plus this part, plus this part, plus this part, plus this part. Now, is the lateral surface of a cone like this? No, it isn't. It's a straight line. It's this blue line in here. So you're neglecting this stuff in here. You're neglecting this. You're neglecting this. You're neglecting what you can't, and that's why it doesn't work. Okay. So actually, what you're gonna have to do is a little bit more complicated this time. And I'm gonna do this for you guys here. So we have to. Well, I'm gonna relate this time. I'm gonna find all the x with respect to y because we're still integrating with respect to y. Okay, so we have x equals that'll be r divided by h times y. We have dx dy because x is a function of y, right? So you have dx dy equals r. This is a messed up r divided by h because it's the derivative of x with respect to y. Good. Now, you see, how do we do this? How do we add these rings? Okay, we're going to be adding. Let me just show you this again. So we're going to be adding the rings in here. Oh, sorry. We're going to be adding the rings in here. Okay. This one, plus this one, plus this one. So you're getting, when you add all the rings, you're going to get all the lateral surface that these rings represent. But you also have to multiply by this diagonal here, and this one here, and this one here, and this one here. And that's what we're going to do. Now, okay, so it's gonna be the integral, okay, from 0, because you're going from 0 here, all the way to r, all the way to h, of, what is the circumference of each one of those rings, which is a circle? It's 2 pi r, but it's not this r, because this r here, you already got it here, that's not this r, okay? It's the r for the particular ring that you are, where you're at, for the particular height in here. So the r in here is going to be this length, the r in here is going to be this length, the r in here is going to be this length, so the r is going to change, okay? So what is the r again? Well, the r is x again, so we're just going to plug this in here, okay? So it's 2 pi r, but it's not r, it's x, but you can just plug x in here because you're integrating with respect to y, all right? So you have to put this as the x as a function of y. Yeah, I know it's complicated. And now it's going to be 2 pi r divided by h times y. So r divided by h times y. Great. Now you have to multiply by these little pieces in here. Okay. Now what is this? This thing here, how do we find the length of this stuff? Well, you can say, well, if you're going to multiply by this piece and this piece and this piece and this piece, so it's just this whole thing here. Okay. It's going to be this length. And what is this length? It's the square root of r squared plus h squared, right? Because you have this, can you see that this thing right here is a right triangle? Okay, so if this is a right triangle, okay, then this is going to be one of the regular sides, this is going to be the other regular side, and this is going to be the hypotenuse. So what is this length in here? It's the square root of the sum of the square of the other two sides. But you can't just plug it in here because this is not related to y. You have to relate everything to y. This is just a constant. This is the radius of the base, which is a constant, and this is the height of the cone, which is a constant. So you have to relate this stuff to y. So you can't just write it like this. You're going to have to relate this to y. Now, how do you do that? Remember that we're integrating with respect to y, and when you do that, you want to find the length of a curve. What do? You do, well, it's already an integral. This is already an integral, so it's going to be the square root. Ooh, yeah, it's going to be the square root of 1 plus, we're integrating with respect to y, right? It's going to be one ring here, another one, another one, another one, in this direction, in the y direction. So we do this here. dx dy, oh man, dy, okay, squared with respect to dy. I don't know why this is happening. There you go, with respect to dy. Now you can integrate this stuff and you're going to find the lateral surface of the cone. Okay, now this is going to be such a mess. I'm just going to simplify a lot of this stuff in here. Okay, you can, whatever is a constant here, you can get out. You can get it out. So get out of what? Get out of the integral, okay? So 2 pi times r divided by h, okay? None of this stuff in here depends on y, on dy. It doesn't change. As y changes, pi is going to be pi, the radius of the base is going to be the radius of the base, and the height of the cone is going to be the height of the cone. Okay, now this stuff in here, I'm just going to simplify. Okay, what do we have here? We have that stuff in here. Okay. So what is this equal to? I can say that this whole thing equals, well, you have dx dy squared here. What is dx dy? It's r divided by h. So you can say the whole thing, okay, is r squared divided by h squared. Plus, but you see, I want to unite these two plus 1 over here. But how can I make this 1 have a denominator? Because I want to join the fractions together. I want to put them together. I want to use this denominator. So how do I put a 1 in here? I do this, okay? This is the same thing, guys. H squared divided by h squared plus r squared divided by h squared is going to be equal to what? 1 plus r squared divided by h squared. It's the same thing that you have over here, okay? Oh. Okay, so I'm going to undo this mess in here. Okay, so this equals that. But the problem is, well, see what you can do here? You have the square root of a fraction. So you can take the square root of the numerator divided by the square root of the denominator. Now, what is the square root of the numerator? Well, it's h squared plus r squared, and that's the square root of that. So it's going to be this length in here, right? It's r squared plus h squared, and you're taking the square root. So it's just going to be this length in here. So we call this thing here, in Portuguese, people call this the geratriz, the geratriz. I don't know if they have a similar term for this stuff in English. Okay, but it's just this length of the cone here. So people call that stuff G. So this stuff in here, the numerator is G, and it's not going to change. Okay, not according to Y, it's G and that's it, because it just depends on the radius of the base and the height of the cone. So you put a G here. Okay, and now what do you have here? You have this thing here already got. Just have this in the denominator, the square root of h squared, which is what? H. Okay, it's just this thing here is just this. Of course, you got to put a G here. Okay, so this equals that. But don't worry about the G. You're just worrying about the denominator now. So it's the square root of 1 here, whatever it's in here, over h squared. So it's 1 over h. But you already have an outside h in here. So what do? You square it. Okay, because you already had an h in here, and now you have this one. So you put it over here. So we eliminated this stuff in here. We eliminated this. What's left? Y. Now y depends on y, so it's going to be y dy. Look at that. Thank God. I'm going to continue this mess over here. So it's going to be this term, okay, and the integral of y with respect to dy, so which is going to be what? Y squared divided by 2. Okay, you have to plug in. Now, what's the limit of integration? The limit of integration is from 0 all the way to h. Okay, so if you plug 0 in here, it's just going to be 0 divided by 2. Don't worry about that. Now, if you put an h in here, what are you going to be left with? You're going to be left, well, it's not equal. I'm going to get this equal out of here. I'm just trying to simplify things. So you're going to be left with h squared divided by 2. Now, this h squared divided by 2 is multiplying this whole thing. Okay, so this h squared here, you simplify with this one. This 2 here, you simplify with this one. And what are you left with? You don't have the integration here anymore, right? We've already integrated. So what are you left with? Pi rg. And pi rg is the surface, the lateral surface area of a right cone. Only of a right cone. Okay, if the cone is not right, then the surface area is going to be larger. Even though the volume is not going to change, the surface area is going to be larger. So the surface area of a, I'm going to put a right cone in here like this, equals pi rg, where g is what? G is the square root of h squared plus r squared. And that's it.